Hey y'all, welcome back to Alakazam Math Made Easy. By this point, a lot of people have had their first derivatives exam, so I hope that went well for all of you. But just as a recap of what we've gone over so far, so by now we know what the formal definition of a derivative is. That's covered in video 10. We know a list of some of the most common derivatives, or the derivatives of the most common functions. That's in videos 11, 15, and 17. We also know common derivative rules, right? Product, quotient, and chain rule. Those are in videos 12 and 16. And lastly, we know some basic applications, and we started covering that in video 18, but the largest chunk of applications will happen in this next module. So the content between derivatives review part A and derivatives review part B. So what do we have in common with all four of the things we know so far? That would be that the function needs to be somewhat simple in the sense that we should be able to identify where these rules exist, but most importantly, we can only follow the information in these four steps if we can fully separate the x variables and the y variables. So what happens if we can't do that? That's where the topic of implicit differentiation comes in. So implicit differentiation, like from a not necessarily math standpoint, means that you're differentiating essentially indirectly, right? So there's going to be an extra step to get it to the form that we need it to be, which is y prime equals something. So I'll go through a couple examples so you know what I mean by this, but every time, so first of all, the equation won't be y equals whatever. But you still go through each term of the equation, right? So you'll have multiple terms, you go through each one. Every time you take the derivative of a term that has a y, attach a y prime. And like I said, I will go over this in this first example. But also I want you to remember that even though it looks different, all of the same rules apply, right? Quotient rule, product rule, chain rule, all of those still apply. So you should still keep an eye out for some of the telltale signs that you'll need to use these rules in these problems, even though they're not set up exactly the same. So this first example, right, is, I'll write it out again so it's easier to see. It's x squared y plus xy squared equals 3x. And you should know that this is implicit differentiation because there's no way for you to rearrange this very easily to be y equals everything else, right? So instead of wasting your time doing that, it'll probably be easiest to just work through it implicitly. And remember how I said with implicit differentiation, you take the derivative of each term, right? And that's what we're going to do. So the first term is this purple circled x squared plus y. So we're going to pretend everything else doesn't exist, and we're just going to look at that. So x squared times y, we said times there, right? So that has to be product rule. We have two functions, whatever x is and whatever y is. So we're going to do that as product rule. So remember, product rule, we take the derivative of the first piece, which is this x squared. So that's 2x times y, because we're doing v left alone. So there's that piece, plus this first chunk left alone times the derivative of y. And I know previously y has been the name of the whole function, right? Y equals some combination of x. But in this case, y is going to be treated like a variable, right? So if y was a, the derivative of a would just be 1. So we're going to do the same exact thing. Y is a variable. So the derivative of that is going to be 1. And because we're taking the derivative of a term that has y in it, we're going to attach a y prime. That's what I meant by that. So we'll jump then into the next term, which is x times y squared, which again, we said times, so that's product rule. The first step is to take the derivative of this first chunk, that's where this 1 comes from, and then we leave y squared the same because that's our v term. And then the next step would be to add the first term left alone times the derivative of that second piece, which is 2y. Because remember, y squared is just a variable, just like an x would be. So y squared becomes 2y, but we attached that, we took a derivative of the y, so we have to attach that y prime. The last piece we have to look at is this 3x piece. Which is pretty straightforward. 3x is the same as 3x to the 1 The 1 multiplies to the front becomes 3. X to the 1 becomes x to the 0, which is just a constant. So that last piece becomes just x, or I'm sorry, just 3. So what we're going to do is we're going to combine this by replacing essentially everywhere we took a derivative, we're going to put its derivative and then just plug everything else in to the function that way. So like I said, we'll just add all of the derivatives together basically and set it equal to this one over here. So we have the derivative of that first term plus the derivative of that second term equals the derivative of that third term. And then, so that looks great, excellent. But that's not what derivatives look like. Derivatives are y prime equals something. So how do we get it equal to y prime equals something? So the first step is we move everything that has a y prime in it to one side of the equation. So if you look, all of these terms have a y prime, all of these terms do not. And what that'll allow us to do is that'll allow us to essentially factor out that y prime, which is nice because then we can divide everything that isn't the y prime. So everything in here, we can divide to both sides, right? Which would mean it would cancel here. And then we can get this, which is y prime equals something that's going to be very ugly, but it still is y prime equals something. So that's still valid format to write the derivative. I will let you know that a lot of professors will not accept an answer in this form. A lot of them will only call a correct answer if it's in the y prime equals something form. So that's my recommendation there, is get really used to writing those in that form, but it's literally the same steps every time. Put all the terms that have a y prime to one side, factor out the y prime, divide everything else, it'll get you into that format. So another way to write one of these questions would be to find the slope of the tangent line of the following function at the point given, right? And that's what we want to, that's what I'm going to do together. So remember, we go through all of these terms as if it is, you know, one at a time. X squared becomes 2x, and we have minus, this is going to be product rule, right? So derivative of the first one times the second one left alone plus derivative, or first one left alone, times derivative of the first one, or derivative of the second one, my bad. Hard to write and talk at the same time. And then we'll move right on to this next piece, which becomes 2y, but again, because we took a derivative of a y term, it has to be equal to, or we have to attach that y prime, and then the derivative of 7, because it's a constant, becomes 0. So we have 2x minus y plus xy prime plus 2y y prime equals 0. What we'll do is we'll distribute this negative into here. So it'll be negative xy, which will allow us to say, all right, now this term and this term are our y prime terms. So everything else will move over to that side. So we have negative xy prime plus 2y y prime equals negative 2x plus y. And like I said, every single time you factor out a y prime. And then we'll divide both sides by that other piece. And then we'll get y prime equals negative 2x plus y over negative x plus 2y. But, so that's the derivative, right? But it's asking us for the slope of the tangent line of the following function at the point 1, negative 1, 2. So just like if we were to take the derivative of a function and plug in the value for a, if it was asking us before to find the slope of a tangent line, we would plug in the x value. Here our function is asking us for, our derivative function has both x's and y's, so it gave us a whole coordinate, like an xy coordinate, to help us solve for that slope. So again, y prime is literally just going to be plugging in the given values. Over negative That's going to become positive 1 plus 2 times 2. And that's going to get 2 plus 2 over 1 plus 4. That's going to be 4/5. It's going to be 0.8. So exactly the same process as we did before to get to here, right? So we found the derivative of each term, and then we moved all of the y prime terms to one side, divided by everything that wasn't a y prime to get us to here. That's our actual derivative function. But it was asking us for the derivative at this point. So just as we would before we had introduced implicit differentiation, we plug in the values we need to get to a whole number. Because we now have x's and y's, we need to plug in a value for both x and y, right? So that's why we now have a whole coordinate as opposed to just an x value. So my recommendation for this specific topic is just practice, because it's going to be one of those things where you're not going to be able to memorize it because it'll be different every time. So you're going to end up learning it by practicing it. The good news is every single step is the same for every single problem. So that'll be hugely beneficial because it'll become muscle memory. If you learned something from this video, give it a like. If you still have questions on implicit differentiation, leave it in the comments. I'll answer them as soon as I can. If you want to stay up to date when I post new videos to this channel, feel free to subscribe and turn on your notifications by hitting the little bell looking icon. But other than that, best of luck.